In this video tutorial, we'll be looking at how to create scenes in Maestro. By the end of this tutorial, you'll be able to understand the benefits of using scenes to tell a story and save, view and manage scenes in Maestro ready to send to Pymol. First of all, why are we using Maestro in the Visualizing Science with Pymol 3 course? Maestro is Schrödinger's visualization interface, and it enables scientists to run both basic and complex workflows and calculations, from structure preparation, docking and virtual screening, biologics and material science workflows, through to advanced molecular dynamics applications. We're going to begin this tutorial within Maestro since many researchers do their science in Maestro and then may want to share their findings and show off their science to the world using Pymol. If you're unfamiliar with Maestro and interested in learning more, check out our free Getting Going with Maestro video series, or one of our introductory level online certification courses, where Schrödinger software access is provided via a virtual cluster as part of the certification course fee. If you have Maestro installed and you're following along, let's get started by launching Maestro and setting the working directory. Next, come up to File and Open Project, then navigate to the Pymol 3 course data directory and open the HTVS AMP-C PRJ zip project. Save this project. I'm going to call it HTVS AMP-C Scenes. The entry list on the left is similar to the contents panel in Pymol, and we can see that there are a number of entries and grouped entries in this project with different names. These entries are the result of a target validation and preparation workflow, and the 1L2S structure is the PDB ID for an AMP-C beta-lactamase enzyme, which is in complex with an inhibitor. And this inhibitor was identified via a high-throughput virtual screening docking approach. To learn more about this structure, check out the Protein Databank entry and the original publication, and to get hands-on with the virtual screening workflow, check out our high-throughput virtual screening for hit finding and evaluation Schrödinger online certification course. The first entry in our entry list is the original PDB file, not yet prepared. We're going to start our scenes-based story with this in order to communicate some of the key structural inspection and preparation steps that are undertaken prior to initiating a structure-based virtual screening workflow. Make sure that only this first entry is included in the 3D workspace, and use the Fit to All Visible button or type Z on your keyboard to ensure that we can see the whole structure here. Now come up to Workspace, then Project Scenes and choose New. The new scene dialog opens and we can enter a description of this scene here. Let's call this 1L2S Original PDB, then click OK. We have only saved a single scene right now, but if we zoom or modify the view, we can at any point come back up to Workspace, Project Scene and View, and this will take us back to the saved scene in the scene viewing mode, with the description we entered below the 3D workspace. Click on the Exit Scene button to come out of the scene viewer. In Maestro, the next step after importing a PDB is protein inspection and preparation, which at its most basic level includes addition of hydrogen atoms in accordance with specified global pH, refinement of hydrogen bonding networks, and a gentle minimization. As we saw in an earlier tutorial, we can add hydrogens in Pymol, but Pymol adds hydrogens according to heuristics with no understanding of global pH, local pKa, or the orientations of other hydrogen atoms. To learn more about protein preparation in Maestro, check out the Schrödinger documentation webpage, and there are hands-on examples in a number of our online certification courses. In this example Maestro project, we have carried out the protein preparation, so let's go ahead and include the prepared 1L2S prepared A hollow entry below the 1L2S A chain group header to take a look at what this means. Comparing this entry to the original PDB, we can see that the chain A entry contains a single copy of the AMP-C beta-lactamase structure, whereas the original PDB entry is a homodimer, that is, two chains of the same protein. As part of the preparation process, these chains have been split into separate entries, aligned and grouped for ease of comparison. We can also see that hydrogens have been added and states have been assigned depending on the net charge and the location of protons. Some residues, such as histidine, can adopt multiple states. With histidine, we may see HIP, which is +1, both delta and epsilon nitrogens protonated, HID, neutral, delta nitrogen protonated, and HIE, neutral, epsilon nitrogen protonated, whereas the default is HIS. In Maestro, any state changes or flips that have occurred during the protein preparation process will be labelled, for example HIE, HID, or flip. Using the mouse or trackpad, let's find a nice view of this prepared structure. A reminder too that you can customize your mouse controls in Maestro via the Workspace Customize Mouse Actions menu, and you can even use PyMol mode here. When you're happy with how things look, come up to Workspace, Project Scene, New, and let's create a new scene called 1L2S Chain A Prepared. Then click OK. Next, let's zoom in on the binding site using the Fit View to Ligand button, or L key on the keyboard, and then use the Interactions toggle in the lower right corner to display the key protein-ligand interactions. Adjust the view as desired, then come up to Workspace, Project Scene, New, and let's call this scene 1L2S Chain A Ligand Binding Site. Then click OK. Next, let's find and zoom in on the asparagine 289 binding pocket sidechain, and either toggle off the solvent in the structure hierarchy menu or use the 1L2S prepared A hollow dry entry. It is important to inspect potential histidine, asparagine, and glutamine flips after hydrogens have been added and hydrogen bonding optimization has taken place as part of the structure preparation process. We're going to add a residue label and create a new scene to reflect this, as these kinds of changes in a binding pocket can have profound effects on computational modelling experiments, such as virtual screens or free energy calculations. Finally, we have some watermap results in this project. Click on the arrow next to watermap results to expand the group if it's not already open. Watermap is a molecular dynamics approach that is used in structure-based drug discovery projects to determine hydration site thermodynamics. The method can identify potential potency handles, enabling researchers to screen for or design novel binders that may displace or stabilize water molecules in certain regions of the binding pocket. Click on the W next to the Watermap 1L2SA APO Watermap entry to launch the Watermap Examine Results panel, and check out the associated Schrödinger documentation page and Watermap manual for more information, or enroll in our HTVS online certification course for a hands-on tutorial. The Watermap Examine Results panel is now populated with data, and the Watermap is displayed in the workspace along with the small molecule ligand and receptor. Although the ligand is displayed here, it was not included in the calculations. It is, however, useful to have this ligand overlay present when analysing the hydration sites. From the drop-down site label menu, choose Free Energy. We can see several orange and red spheres, and we can see from their free energy values that these are very high energy hydration sites, meaning they are highly unstable. We can also choose to display only the highest energy hydration sites by moving down the Watermap Examine Results panel to Show Only Water Sites with and checking the free energy box, then changing the value at the left-hand side of the slider to a positive value. Let's start by changing this to 3. Now we can see the highest energy hydration sites present in the apoprotein displayed as red spheres. We can see from the ligand overlay that several of the high energy hydration sites in the binding pocket are likely to have been displaced by the ligand. And this is great because it implies that a drug-sized molecule that can be accommodated in this binding site will receive significant binding affinity from simply occupying the binding site, thus confirming the target's drugability. Let's create a scene displaying these watermap results and call it 1L2S Chain A Watermap High Energy Hydration Sites. Great. Now that we've created a number of scenes, we can review them and make edits if needed by coming up to Workspace, Project Scenes, then Manage. We can click through the thumbnails to sync up the selected scene with the 3D workspace, and we can see that we've done a fairly good job of describing these various views. I'm going to click and edit binding site in our third scene and rename this binding pocket for consistency. We can also select and delete scenes here, or drag to swap the order. Projects in Maestro autosave, but now we've created the scenes we care about, we might want to share our project with a colleague. Come up to File and Save Project As to save this as a read-only archive type. We can now send this project to a colleague and they'll be able to open it and view the scenes. Okay, so that's how we create scenes in Maestro, and we can see how this can be really valuable in telling a story both in terms of our structure of interest, and in this case to communicate the computational methodology or workflow. The aim here was to use Maestro to highlight and save some key scenes that we might want to include in an animation or movie to communicate our science. And in the next video, we'll be using this same project and looking at how to send these scenes to Pymol to easily create a simple movie in just a couple of clicks. That brings us to the end of this tutorial. You can now understand the benefits of using scenes to tell a story and save, view and manage scenes in Maestro ready to send to Pymol. Thanks for watching.